Hi everyone, it's Miss H, and today we're going to be looking at waves. Specifically, we're going to be looking at types of waves today. We'll look at other things related to waves in further videos. So let's start out with what is a wave. A wave is a disturbance that travels through space. You'll oftentimes hear it described as a disturbance that travels through a medium, but not all waves require a material to travel through. So I prefer a disturbance that travels through space because some waves can travel through the vacuum of empty space, and some waves require a material to travel through, and we'll talk about that difference later. It's important to remember that waves transfer energy, they do not transfer matter. So even when it is traveling through a substance, the material itself pretty much stays in place. It just kind of vibrates back and forth, but the energy continues to move through. There are two ways that we classify waves. The first way is by how they move, and when we classify waves by how they move, there are three main types of waves. The first is called a transverse wave. With a transverse wave, particles travel perpendicular to the motion of the wave. An example of a transverse wave would be an earthquake wave, or an earthquake S wave rather. So this is what we're going to call the normal rest position. So this is how the material would be if there was no energy moving through it. So once the energy moves through it, then you have the wave that looks like what I just drew. So that wave is our disturbance. So our particles are the ones that are moving up and down, whereas the energy is traveling from left to right across the screen. Now, ideally, I would have drawn this so that everything was perfectly level. That's not what I wanted to put yet. And so that all of these had the same height to them. So the top of this is called the crest, and the bottom is called the trough. That's T-R-O-U-G-H, trough. If we measure the distance from the crest to the trough, or from the crest to the normal rest position rather, the distance between the crest and the normal rest position, or the trough and the normal rest position, is called the amplitude. The distance from the top of the crest to the bottom of the trough is called the wave height, and that's something that doesn't really matter much for us. If we measure the distance from crest to crest, from trough to trough, or from one position to the next like position on the wave, we call that the wavelength. Okay, these are all terms that are going to be very important in future videos about the properties of waves. So it's important to know all of these different properties of a transverse wave. Okay, our next type of wave by movement is called a longitudinal or compression wave. With a longitudinal or compression wave, the particles travel parallel to the motion of the wave, and an example of that would be an earthquake P wave. So what we have here are the parts of a longitudinal or compression wave. So the spread out areas are called rarefactions, and the squished up areas are called compressions. And just like on our other wave, we do have an amplitude, such as going from the beginning of one, or the end of one compression to the end of the next compression, or the beginning of one rarefaction to the beginning of the next rarefaction. That would be our amplitude as well, or our wavelength rather, sorry. That'd be our wavelength, not our amplitude. That'd be our wavelength. So again, here the particles are moving back and forth, left to right across the screen, and the energy is moving back and forth, left to right across the screen. Okay. So again, that is also, that distance right there is also our wavelength. Okay, the final type of wave by movement is a surface wave. With a surface wave, the particles travel in a circular pattern. Examples of this would be ocean waves or earthquake surface waves. So the particles actually move around in a circle, but again, the energy is going to move left to right across the screen. The other way that we classify wave type is by how they are transmitted. And when we classify by how they're transmitted, there are two main types of waves. The first is an electromagnetic wave. Electromagnetic waves are always transverse waves because transverse waves can travel through a vacuum, whereas longitudinal waves cannot. So electromagnetic waves are always transverse. They are actually capable of traveling through a vacuum. Electromagnetic waves are how we get our energy from the sun. They are produced by changing electrical and magnetic fields. And examples would be light waves. All light waves are electromagnetic waves, and they're always transverse. So when we talk about light waves, we have to talk about the electromagnetic spectrum. So what is the electromagnetic spectrum? The electromagnetic spectrum is where you take all of the possible wavelengths and frequencies of light and arrange them in order from longest to shortest. So when we put our electromagnetic spectrum in order from longest to shortest wavelength, our longest one extreme end, our longest wavelengths, lowest frequencies are our radio waves. So our longest wavelengths, lowest frequencies, those are our radio waves. They are capable of traveling the longest distances, and because of that, they're frequently used for communication. Radio waves oftentimes have distances that are kilometers long, but they can just be a few meters long as well. Radio waves include using radar as well. Excuse me. So next we have microwaves. Some people consider microwaves to just be short radio waves, but we actually do separate them out. So microwaves are shorter than radio waves, longer than infrared waves, which are the next ones, but they are used in microwave ovens for cooking. It is actually perfectly safe to stand in front of an intact microwave. Old original microwaves that were used in research facilities didn't have that shielding on the front. So if you look at a microwave now, you'll see the little dot pattern. That's shielding on the front to make sure that those waves stay inside the oven. The spacing of those dots has to do with making sure that the waves can't escape. So as long as your microwave is intact, it's perfectly safe to stand in front of it, but you can also just be on the safe side and choose not to. So microwaves are shorter than radio waves, longer than other types of waves. Next we have infrared rays. Okay, infra means below or under, so these are just a little bit longer than the red waves of visible light. Infrared, the biggest thing here is that this is associated with heat. This is actually the heat that we get from the sun. This is when something is giving off heat. It is in the infrared spectrum. So next we move up to visible light. Visible light is of course what we're most familiar with because it's what we can actually see with our eyes. Visible light breaks down into red, orange, yellow, green, blue, violet. That goes from longest wavelengths to shortest wavelengths. And they each have, we're getting into nanometer wavelengths. So this is getting much shorter. So we've already gone from kilometers to nanometers. So we're getting very, very short very quickly. If you combine all of the colors of visible light, you end up with white light. And if all of the colors of visible light are absorbed by something, it looks black. Moving further up, we get to ultraviolet rays. Ultra means above or beyond, so these are a little bit shorter than the violet end of the visible light spectrum. Ultraviolet, even limited exposure, is good. That's how we actually produce vitamin D in our bodies. We need that ultraviolet exposure to be able to produce enough vitamin D. And lack of vitamin D can lead to things like depression, so we want to make sure that we are getting some UV radiation. But we all know about cancer and skin cancer, so we all know that it's important to limit our UV exposure. Ultraviolet rays can also be used for disinfection purposes and that sort of thing in industrial settings. And of course, agriculture, we wouldn't be able to have our crops without ultraviolet because ultraviolet is what sparks the photosynthesis in plants. So as we continue moving up, we end up with X-rays. Even limited exposure can pose a minor risk, which is why they put that lead shielding apron on you to protect your most vital organs when they're taking an X-ray. And why things like the X-ray tech will step out of the room. And of course, long-term exposure can be very dangerous and cause severe damage. This is why we no longer have things like X-ray machines at the shoe store to check the fit of our shoes, and we now use our finger to push down and figure out where our toes are instead of sticking them in an X-ray machine. But it's perfectly safe in small doses for things like diagnosing a broken bone or transportation settings, walking into a courthouse, something like that, and having to pass your bag through the X-ray machine, all of those sorts of things. So again, it's used in medicine, industrial settings, and transportation for inspection purposes and checking for things like broken bones or cavities, that sort of thing. And then finally we get to our shortest wavelengths and highest frequencies, which are our gamma rays. So these are the most dangerous. Even a very short-term exposure can be highly dangerous. This is something you don't want to mess with unless you absolutely have to. It is used in medicine for treatment of things like cancer and that sort of thing, and it can be used as an industrial inspection tool when you're talking about infecting things like metals that would stop X-rays. Unfortunately, though, it does not turn you into the Hulk. It does not give you superpowers, so don't mess with gamma rays. Okay, the other type of wave by transmission method is a mechanical wave. A mechanical wave is not capable of going through a vacuum, which means that it does need material to travel through. Solid, liquid, or gas, doesn't matter, but it has to have some form of material to travel through. It can be transverse, longitudinal, or surface, so mechanical waves can be any type of wave except that they cannot go through a vacuum. The most common type of example of a mechanical wave that we'll look at in this class will be sound waves. So that gives us an overview of our types of waves and how they're transmitted. Next, we're going to be looking at how we do calculations involving waves.